You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that had, has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you. Hello, this is Richard Jacobs with the Future Tech Health Podcast, and I have Richard G. Bauer, professor at the University of Durham, and he's researching observational and theoretical cosmology. So I'll leave it at that and let him to describe more of it. So, Rich, thanks for coming. How you doing?
I'm doing very well, thank you.
Yeah. So tell me about your research and your work. What's it about?
So the easiest way I found to describe what I do is to say I make the universe. Well, maybe not the universe, but a universe. So what we try to do is we take the laws of physics, what we know about how the universe started, the theory of the Big Bang, and then we use a huge supercomputer to evolve the universe and to see if what we understand about the laws of physics creates a universe that actually looks like the one we see around us. And we've had some big successes with this. Our recent calculations, the universe looks very much like the universe that you might look at with a telescope. So this has been very useful, very interesting research.
So you're trying to model the universe just in your mind, or actually somewhat physically somehow?
Well, it's a mixture of both. So what we're trying to do is to use the computer to do calculations. So we can't make an experiment that physically makes a universe, but what we can do is program the computer, describe the laws of physics in terms of mathematical equations, and then use the computer to solve these equations. So typically we think about the computer simulation as moving particles about that represent elements of mass or groups of stars. And we can calculate how, for instance, the force of gravity moves them around, figure out how they would move, where they would go to, and where they would end up. And our calculations go much beyond that, because as well as moving the particles around, we teach the computer about how stars are formed. So how parcels of gas collapse to make stars, how those stars explode and produce energy and heat up all the gas that remains around them. And sometimes these processes lead to the formation of black holes. So we teach the computer about that. And we put all of these elements together into our calculations, described in mathematical terms, and then realized by calculating this on the computer. So you can't physically touch what we have, but you can explore it in many different ways.
Yeah, what does the output look like? Is it visualizations of what's going on, or is it just purely numbers that are coming out of it, and then you have to take those and render an image, or are you looking for, I don't know, what are you looking for in the data? What does the output look like to you?
So one of the beautiful things about the data is you can look at it in many different ways. So in some ways, what we care about are numbers. So when we look in the night sky, we can count galaxies that we see. That was something Herschel started doing with some of the first telescopes. We're doing it more and more accurately as we build bigger and better telescopes. So that, you measure for galaxies of a certain mass, you count how many there are in the sky, in a volume of sky. And in terms of hard numbers, we then go to the simulation and we count for galaxies of the same mass, how many are created in the simulation. And that's one of the fundamental ways we judge whether the simulation is realistic or not. Have we produced something that the counts of galaxies are similar or close to what we measure in our own universe? But that's kind of a boring mathematical approach. Well, the other way we can look at the universe is to leap inside it and to visualize what the numbers mean. And so we've done work with various artists, taking these computer universes and then embedding a camera inside the universe and seeing what would it be like if we were living in this computer universe and looking out with a telescope. What would we see? And so those are very interesting, have allowed us to understand much better the way structures are formed, the way the exploding stars that happen in galaxies and their black holes shape the universe we see around us. But they've also been very interesting to create interesting artwork. So one of the things that we've done, one of the most interesting projects that I've had the opportunity to be involved with, was to be part of a team that built that illuminated Durham Cathedral. Now, Durham is a very historic place in the north of England, and it has one of the first large cathedrals in the world, if not the first. And every couple of years, the city is shut down and art is installed all over the city. And we had the opportunity to do a large-scale piece of art in which we projected images onto the side of the cathedral. And we were able to use that to tell people the story, both the history and the way the universe was created, but also mixed and cut together with images showing how mankind had understood the universe and the way our understanding had developed over human history. And so that was a tremendous artwork. It was a real privilege to be involved with the people that created that, as well as the images. There was a soundtrack to go with it. And it was an amazing, moving experience, seeing huge crowds of people, thousands of people crowded in front of the cathedral in Durham to see essentially something that only existed inside the computer. So it was very interesting. That was a really good moment.
The first step really is to accurately model whatever you're looking at, a galaxy or the whole universe or a solar system.
Yeah.
I mean, how close do you feel like you've gotten? I don't know much about it, but I thought dark matter and dark energy is such a gigantic, confounding thing that it would make any model, I don't know, inaccurate, or can you account for it? And can you accurately model what you're looking to model in the first place?
Well, one of the really interesting questions in physics at the moment is whether we understand what dark matter and dark energy are. And there are very clear front-running theories for these. So let me start with dark matter, because I think that's by far the least contentious. So when we look at the universe and we measure, for instance, how fast galaxies spin round, we can see how fast they spin. And rather like if you were spinning a stone around on the end of a string, you would be able to figure out how much tension there was in the string. So we can do that calculation, but then we compare it to the amount of mass that's providing that tension. And if, according to standard theories of gravity from Einstein, from Newton, we could measure how much mass there is, but then we compare it to the mass that we actually see, the mass in stars, and we see that there's a huge discrepancy. That more or less 3/4 of the mass we see is missing. And so people have tried various explanations. Oh, well, this could be mass in stars that are so small that they don't emit much light. It could be in the form of rocks. It could be other things that we just don't see. But it turns out none of those work, and we can show that those theories don't work. So the conclusion you're forced to is that this mass must be some form of matter, but it's not made up of the elementary particles we know about. So it's not made up of neutrons and protons that form normal nuclei. It's not made up of the more exotic particles that might be made at the Large Hadron Collider. It's something else. And it got this name, dark matter, but maybe it's not really so mysterious, because the more we learn about the particles that make up the matter that we know about, the more experiments we do at CERN with the Large Hadron Collider, the more we discover that it seems that the particles we know about are just half the particles that are predicted by these theories, and that there are maybe equivalent other particles that are often called supersymmetric particles. So,
how do you? Quick question here: how do you model the fabric of space in your universal models? Do you just assume it's vacuum, or do you assume that there's something there? Or?
Well, and that leads us on to the question of dark energy, actually, very, very neatly. So. Einstein had a great theory of gravity, and it's essentially Einstein's equations that we use to calculate the forces of gravity. Or if you equivalently, Einstein would have us think about distorting the space-time fabric of the universe. So we can calculate those distortions. Now, one of the big challenges in physics at the moment is that Einstein's theory of gravity sits very uncomfortably with the theory of quantum mechanics. And it's very hard to see how these two theories can be compatible. And one of the things that's predicted by the theory of quantum mechanics is that empty space can never actually be empty. And so you would expect empty space to have this strange vacuum energy. In other quantum systems, we see the presence of this vacuum energy. There are many experiments, the Casimir effect, which demonstrate that it's really there. And so you can think of this as making a correction to Einstein's equations, and that correction would look just like dark energy. So there's maybe a well-motivated idea that if you model the fabric of space-time using quantum mechanics as well as Einstein's theory, you would explain what dark energy is. And there's one catch to this, though, that if you take what we know about particle physics, what we know about the normal matter of the universe, reasonable theories for the nature of dark matter, you would expect the cosmological constant, or the dark energy, to be around about 10 to the power 60 times larger than we see it. So that's 10 followed by 60 zeros error in this calculation. So everyone is a bit puzzled about this. Clearly, there's a great theory here, but something very fundamental is wrong with our understanding. So that's the big challenge, perhaps, with what we know about the universe at the moment, is we can explain a mechanism that would create dark energy, but we can't explain why it is as small as we observe.
What could be the possible mechanism for creating it, and what would it be like?
Well, it's just a fundamental constituent in the nature of empty space. So essentially, in quantum mechanics, if you try to make something empty, it will still contain particle-antiparticle pairs. So like a particle and its opposite can be spontaneously created from nothing. They exist for a short period of time and then disappear. So over time, the space is sort of on average empty, but the energy of that space is not zero. And so that small difference mounts up as you look on larger and larger scales of the universe. So during the Big Bang, this dark energy is completely negligible. It's space is full of normal forms of energy and matter. But as the universe expands, becomes more and more and more dilute, eventually we get to a point at which the dark energy becomes comparable to the energy in normal matter. And then the future course of the universe changes very dramatically. Now, one of the big puzzles that we have, and has always seemed very strange to me, is the moment we're living and observing the universe is that moment where the dark energy and the normal energy of the universe become comparable. And I don't like coincidences. Maybe it's just a coincidence that humans are in the universe at that moment, but I find that a very uncomfortable explanation. I don't have a better one at the moment, but it's a very uncomfortable explanation.
I mean, I don't know. Is there anything we know about dark matter or dark energy? How could it have formed? What is it made of? Why can't we observe it? How could it take up such a substantial portion of our calculations?
Yeah, so we know for dark matter, we know quite a lot. And indeed, theories of how it's produced people have made up such theories. They're called supersymmetric theories of matter. And those theories have been calculated in a lot of detail and can explain the abundance of dark matter in the universe. And what we see with telescopes is not really very at odds with that. Now, the catch, though, why it's still such a mystery is people would like to be able to actually see a dark matter particle. Predicting in physics new things is very uncomfortable unless we can do an experiment and prove that theory was right. At the moment, we can't do such an experiment. And in fact, the experiments are now getting so sensitive that many of my colleagues that work on those supersymmetric theories are beginning to squirm, because they would have expected the theories to have the dark matter particle to have been detected by now. Although it's very hard to find a dark matter particle colliding with a normal particle, we should probably have seen a few such events by now. We haven't. Maybe it's just waiting a few years and suddenly the sensitivity will improve, and then we will genuinely know what dark matter is. But people are worried that maybe there's something more strange going on in the universe. The issue with dark energy is much more puzzling, because although there's this mechanism that would explain its presence, the magnitude of the effect is so much weaker than we would have expected based on a naive calculation. So that's the real puzzle. I can give you my favorite explanation and tell you a little bit about the work that we're doing on that.
Well, what have you learned from your modeling? Do you have a successful model, and have you been then tweaking various universal constants slightly to see what it does? I mean, what use has the model been to you? What have you discovered?
Yeah, so our model is very successful. So if we take what we know about dark matter and dark energy from observations of our universe, doing the calculations that I've been describing, and we put those into our computer universe, we can show that we create a universe that's very similar to what you see with telescopes. So the reason I think we're very successful is I took some of the galaxies we created in the computer to give a talk to some amateur astronomical societies. And these are people that have observed many galaxies in the universe with telescopes that they may have made themselves. They have an observatory that they've made in their backyard. And they know an awful lot about every galaxy in the universe. And it was such a pleasure to show them these computer-generated universes and see that they were arguing about whether they knew which one it was and whether they'd taken a photograph of it. Because that meant that the computer galaxies were so convincingly realistic that people who knew a lot about taking pictures of galaxies than the real universe couldn't tell the difference. So that, to me, that made our project very, very, very successful. I was very pleased with where we'd got to. So given that success, we were then able to ask the question, well, suppose dark matter or dark energy were different. How would that change the universe that we see and how we make of would it help us understand the strange value of the dark energy? Okay, why its value was so small. So we built models and we changed the amount of dark energy, the amount of dark matter, and we were able to explore how this changes the number of stars in the universe. Now, what I was hoping would come out of that project was the answer to the small value of dark energy, because we thought, if dark energy is large, the universe expands incredibly quickly, and that this expansion would lead to the formation of many fewer stars and galaxies. Now, it's true that if we make the dark energy very, very much bigger, it suppresses the formation of stars. There would be nobody in the universe to look out and observe what's going on. But it turns out that we could still have a dark energy that was 100 times what we observe, and there would still be people able to look out into the universe. So it didn't work as an explanation for that aspect of the universe, that we didn't conclusively show the reason dark energy is such a small value is an anthropic reason, i.e., in order to be able to observe the universe, do astronomy, the dark energy has to be small. That argument we can show to be false from our work. And it leaves open then the question, well, either it is just a coincidence that we live at this moment where the two energies are comparable in the universe, or else there's a piece of physics that we really don't understand. There's something more to the universe that we are still needing to discover. And you might hope that that would be some combination, a more fundamental way of combining Einstein's equations and quantum mechanics that would lead you to a back reaction that makes the contribution of quantum mechanics as small and comparable to what we observe. Now, it's great having an idea of what that theory is, but to actually make sense of it, I think that is going to take a lot of work to come up with something that's very convincing and provides that explanation.
But again, what interesting things do you see that are unique to you or new to you, or spark your curiosity based on the results of the model?
Well, so it fires my curiosity to understand how galaxies are created and what makes particular galaxies different to other ones. So when I look at the night sky with a telescope, what I see is this huge variety of galaxies. And some galaxies, for instance, are spiral galaxies that you can imagine are spinning round, and if you do the measurements, you discover they're spinning disks of stars, while other galaxies are round balls of stars, and all the stars in those galaxies tend to be old. So essentially, those are old and dead galaxies, whereas the spiral galaxies are spinning round, forming new stars all the time. If you look at the colors of these galaxies, the spiral ones tend to be blue, whereas the elliptical ones tend to be red. And I've always wanted to understand, for example, what creates that difference. So using the simulations, we were able to investigate this and try to understand it more deeply. And one of the very pleasing things that we discovered is that our simulated universe showed this dichotomy of galaxy properties as well. So we had galaxies which were old and red and very round morphologies, and we had younger disk-like galaxies that were created in the supercomputer calculation. So we then had to do some detective work to find out, well, why? What creates the difference? And the beauty of the computer universe is that you can take bits of physics out and understand and see what the difference is. And what we discovered is that the key piece of the universe that makes this difference is black holes. So black holes were invented by Einstein as an exotic singularity in his theory of gravity, but it turns out that they exist for real. People have now seen black holes. It's recently been imaged, and we've seen the gravitational waves created by merging black holes. But what we were amazed to discover was how important these tiny and very exotic objects play an enormous role in shaping the universe we see and explaining this difference in galaxies. And our work showed that what tended to happen was in the spiral galaxies, star formation happened and was efficient, and as you added more mass to the system, you formed more stars. And you also blew material out of the galaxy. And it stopped material piling up around the black hole in the center. But we discovered as you went through this process, made the galaxy bigger and bigger, eventually you reached a point at which the flow of material into the galaxy was not able to stop, and it would allow material to build up and build up around the black hole. And then there's a strange effect.
Quick question.
Yeah.
So the black hole is accreting matter.
Yes.
That's not creating necessarily a deficit of matter that is then pulling in stuff that's even concentrically further out, right?
Yeah, so the matter that actually gets accreted onto the black hole can be very small because much of the material is taking a time to work its way through the galaxy. But black holes turn out to be an incredibly efficient source of energy. So that seems at odds, with this idea that black holes are black because light can't escape. But matter that falls into black holes on its way down to the Schwarzschild radius releases a lot of energy. And that energy you can see as light in the form of quasars or in jets of radio emission in what astronomers call radio galaxies in the universe. And it turns out that this energy that comes out of the black hole has a very profound effect on the galaxy that's forming. And if you like, is able to heat up the gas in the galaxy so much that it is no longer able to form stars. So there's a tipping point at which you begin to pile material around the black hole, and then suddenly the black hole essentially explodes and sterilizes the whole galaxy. Now, we can see that in these computer calculations, and it beautifully explains that diversity of galaxies in the real universe. So that was one recent inspiring big success of our work. What we're trying to understand now is more of the nuances of different galaxy properties, whether some galaxies might be rejuvenated, start forming stars again, and whether we can see the signatures of that in the real universe, for example.
So I'm not even really sure what to ask you about it, but actually, one question I wanted to ask you: Do black holes move? Are they stationary? And if they move, what do they leave behind? You know, I guess we could assume as they move, if they do, that they eat stuff in their path. But if they move, do they leave anything behind? What's behind them?
So in general relativity, everything is moving relative to everything else. So black holes can certainly move. The reason, if we think of a galaxy, they tend to be stationary in the center, is that they're just so incredibly heavy. And so as they move through the galaxy, they leave a wake of stars that's called, in a process called dynamical friction, that takes energy from the black hole and leads it to spiral in towards the center of the galaxy. Now, a very interesting question is, when two galaxies collide, what happens to their black holes? The black holes will slowly spiral together, and when they merge at the center, do they form an even bigger black hole, an even more massive system, or does one of them in some way get ejected by the effects of gravity very close to the center of the galaxy?
Okay. Has anyone tried to model? I don't even know how you'd model this, but has anyone tried to model empty space, or essentially vacuum? You know, have we been able to send a probe into space and observe if a certain number of particles we think should hit the spaceship or the probe, and less happen or more happen, or the properties of a large amount of space, to see if there are any properties there we can discern?
Well, so essentially we can do that by looking at the way the universe expands, and that's how we've been able to identify the amount of dark energy, which is exactly what you're saying, is the energy in empty space. Now, the problem for doing this more directly and to fly a spacecraft into intergalactic space is it's a long way to intergalactic space. So we're talking about journeys that would have to be, even if we could launch a spacecraft so that it was traveling close to the speed of light, it would take hundreds of thousands of years to reach a piece of empty space that we could collect particles and know about this. So the nearest we've done is to launch a space probe out of the solar system, but that is still well within our galaxy. So for the conceivable future, the best way we're going to be able to do this is by measuring the expansion rate of the universe.
Yeah, I just wonder, even if you got beyond Earth's orbit, again, into the vacuum of space, if we've been able to, I don't even know how you'd observe a large amount of empty space, because I don't know. I guess other stuff coming in from stars and other parts of the universe would dwarf it.
Precisely. So although the Pioneer spacecraft has got out of the solar system, out of the planets around the sun, it's still embedded in the inner parts of the galaxy, what we call the interstellar medium. And we know that contains a lot of material because, for example, it emits light. So it's very low intensity light, only at very certain frequencies. But we know there is quite a lot of material there, and it's far from empty, even in the space between the stars. So if we wanted to look at a completely empty piece of universe, we would have to go a long way outside the galaxy to measure what was there. And supposing hypothetically we were able to do that, we would find that there was a small amount of hydrogen and helium, and most of the space was filled with dark matter and dark energy. But at the moment, we have no way to kind of count the amount of dark matter and count the amount of dark energy. We just have to infer their presence from the gravity we see in these empty regions of space. And so that's the way we're using at the moment to probe dark energy and dark matter.
So your model itself, again, have you tried messing with the constants of the universe, or have you?
So,
have you found any stable configurations that are either very similar or radically different to our own by tweaking the model?
Yeah, so we can do that experiment. Is one of my great interests to explore how different would the universe be if we changed these fundamental constants. And what we discovered is that the existence of stars in the universe is remarkably robust. So if we make very big changes to these constants, make gravity tens of thousands of times stronger, then the universe would never expand and would never be able to form stars and galaxies. But remarkably, even for relatively large changes, factors of 10, 100, the universe still forms a number of stars that is not very different to the number of stars in our universe. And so this is very interesting, this robustness of the universe. It's almost as if the universe and the way the laws of physics are created inevitably form stars. All right, now you can read into that whatever you wish, but it doesn't to me seem that our universe and the numbers that go into it, the fundamental constants, are in any way fine-tuned to create the universe we see. There would be many other possible changes to these numbers and we would still be able to observe the universe.
I don't know if this is a sensible question, but do you see any of the word itself is constant, but are any of them not truly constant? Do you see in running your model forward in time that constants are in fact not constant, any of them, and are changing?
Yeah, so things that we measure in a particular way and we call constants. So a classic one is the Hubble constant, which measures the rate of expansion of the universe. That is not constant, okay? But it fits within a theory where there are, if you like, what we call fundamental constants, like the constant, Newton's constant of gravity or Einstein's constant of gravity. Now, we make an assumption in our model that those are constants. We could change that assumption, but in what way would we make them not a constant? Now, the way we can try to do this then is to observe the universe and measure these constants, like the constant of gravity. In a sense, dark energy you could view as the cosmological constant would be another constant. We can ask, if we measure gravity in the universe when it was much, much younger, is that constant compatible with the constant we measure today? And at the moment, to within an accuracy of around 1%, the constant seems to be constant, not to change and not to evolve. So people are doing lots of work to try and investigate small deviations from being completely constant. But at the moment, nobody has found any positive results. So it seems that the constants of physics really are constants.
I don't know if this, again, this is sensible either, but I've heard various scientists say the universe is extremely finely tuned. Do you see that as true? And was the tuning a one-time thing, or is it a continual, ongoing thing? Do you have any sense of that?
Yeah. No, so this is a very interesting question. So in the ways we've so far investigated, the universe is most definitely not fine-tuned. And that was one of the big surprises from our work. There are some other aspects that you could maybe take as a signature of fine-tuning, certain values of physics that lead to the chemistry that we see in our universe, how atoms and molecules form particular substances. And certainly small changes to the physical constants that determine that would radically change the way chemistry works. But the problem is, without being able to do detailed calculations for different values of these constants, it's hard to work out, well, does that mean this universe can never form anything like a DNA molecule? Or is it just we haven't been ingenious enough to think how information could be encoded in a DNA-like way? Now, so there are maybe some aspects of that lead us to think our universe is fine-tuned, but I'm not at all convinced that it's not a matter of embracing the possibilities of life and other forms that are not reliant on the chemistry that we have in our particular universe.
Okay. Well, what's I guess last question or two. What are some of the milestones that you hope to achieve, in the next year or a couple of years with the modeling? And that would be a really happy result for you.
Well, so we're currently working on trying to simulate a much larger volume of the universe. This is very challenging because as we try to simulate more and more universe, we need bigger computers, we need faster computer codes in order to be able to do the calculations. Now, the reason, why do we want to go bigger and better? Well, we would like to do these tests. I mentioned the test is, we know Einstein's theory of gravity is right to about a 1% level. People are launching satellites to do experiments that would potentially measure deviations at an even smaller level. But the worry is that those deviations could also be caused by the way galaxies form. So what we don't want to do is to launch this satellite, discover that there appears to be something slightly wrong with Einstein's gravity, get very excited about that, and discover, no, it's just the effect of all these processes that lead to the formation of galaxies. So being able to test this very fundamental theory is a very exciting opportunity to us. I'm sure these huge universe calculations and more realism will be really fascinating for looking with telescopes and trying to understand what we see in the universe much, much better. So those are the two things that are exciting me about the future.
Yeah, I guess in looking at the history, it took many, many years and multiple eclipses to even prove Einstein's theory in the first place.
Mm-hmm. Yeah. So to get to the level of proof we have now has taken 100 years, essentially.
And any particular space probes that you're looking to eagerly to see what they'll come back with?
Yeah, so Euclid is going to map the universe and tell us where all the mass is, how galaxies are moving in the different ways. I'm very excited about that, and something I'm working towards is new missions to map the universe in X-rays. So X-rays you think of as something you might go to hospital and have an X-ray to see if you have broken your leg. But it turns out to be possible to see X-rays from all the way across the universe. And it's very exciting because this tells you about galaxies in a completely different way. So we learn things that we currently have no idea about. We learn about how black holes work. We learn many exciting things. And of course, what's really exciting is we can make predictions for these new X-ray observatories out of our models and see whether we got the answer right. So that's a very exciting possibility.
Well, very good. Well, so what's the best way for people to get in touch and ask questions or see some of the work that you've done or some of the images that you've modeled?
All right.
Yeah. What are some of the best ways for people to experience the output of the model, see pictures?
Okay, so we provided a link on the website to go and look at the work we've done as part of the Eagle project. And there we have various animations, some summaries of the science we've done, some of the best pictures, and including an opportunity to fly through the universe as it's created around you. So I love that visualization. It kind of brings home the beautiful structure of the universe. Now, and so I think that is such a good way to picture how things are created.
Okay, well, very good. Well, Richard, thank you for coming on the podcast. And I know these aren't simple things to talk about, but you speak about them at least in a very clear way, so I appreciate it.
No trouble. It's a pleasure.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.